Today we are going to do section 2.1. So first let's do some book staring. First, this is just the answer page. I'm just going to show you, let's see, where's chapter 2? Right here. Okay, here is, I should zoom back a little bit. Okay, that is, where does chapter 2 end? Oh, that's chapter 3. Oh, I'm missing something. All right, that is better. Okay, so that's the entire chapter 2. So I won't be showing you this again for the rest of the chapter. So next we have, this is page 1, all right. Let's see, push a little bit closer. That should be close enough. Okay, that's page, 62, 63. Okay, next, this is 64, 65. Let's see, let me see how I might hold this thing so that things don't fall apart. Okay, here a little bit closer. Am I parallel here? All right. Okay. Okay, next, finally, 66 and 67. Let me grab the side, okay. And then hold this in carefully. That is a little, that should be, let's see, put it in the middle. Okay, that should do it. And now I also want to show you the contents page, because a couple of days ago I was looking up the content because I already forgot where I heard what. Okay, so this is contents page 1. You can also see the preface to the second edition. Okay, just in case you need to remember where we learned what. Okay, that should be it. That's just chapter 1. And also contents page for chapter 2. Let me grab it right here. Let's see, push it in the middle. Let's keep things parallel. Okay, and okay, that's it. So before we start, I want to do a quick review of all the properties of determinants that you have studied back in algebra or something. Okay, they are relevant in this section because we're going to do quite a bit of it. So if you're not fresh on the determinants, here's a quick review. Okay, now first one is that if, well, I added this first one later. That's why it's 0.0. Doesn't mean it's worthless, okay? It just, well, it's just where I stuck it. So anyway, when you have a, what is that? The matrix, and the determinant of something that is added together, you have a row, okay, and it has two things added together. It is the same as the determinant of splitting them up, and then calculate the determinant and then add it together. That will be important. And the reason I put it there, because it was required as in part of the homework. Now the next thing we need, this we mentioned earlier, you can switch determinants. Well, switching rows. Oh, what I mean here is if you switch any two rows of the determinant, however big they are, if you switch any two rows, they will end up being, one will become negative of the other, okay? And next, if you multiply one row by some number, we had mentioned this earlier, then you can, just one row is enough for you to pull out that common factor, say k, and then the determinant will be k times that thing. And that's just how it works, okay? I mean, if you do work it out, then you notice that is a characteristic of determinants. Next, if you're adding multiples of a row to another row, then you will have the same determinant. And specifically, if one row is a multiple of another row, and one row is directly proportional to the other row, then your determinant is going to be 0. Okay, and next, determinant A times B in matrix multiplication, it happens to work out that if your matrix is being multiplied, the determinant of the product of your matrix is the same as multiplying the determinant of each one after you calculate them out. This is convenient sometimes when you have to multiply two determinants together. Then you can just do the matrix multiplication first. And number 5, of course, is that the determinant can be transposed and doesn't change. In other words, you can flip the matrix diagonally. In other words, all rows become columns in order, and then things are the same, which means all these things that we say about rows, it also work for columns as well. Okay, because of this property, because the determinant can be transposed. And then next, the inverse is 1 over determinant of the inverse is when the two matrices are multiplied to be the identity matrix, and their determinant happens to be 1 over. Wait, I didn't see that being necessary here. I don't think. I'm not sure, but whatever. It's here, so I've stuck it there. And then and then next thing is I want to talk about certain properties of cross product calculated by determinant. Well, that just means this isn't actually a determinant, but the cross product, if you remember what that is, it's difficult to remember, so we use the determinant notation to help remember how to calculate the cross product. That is, we will calculate the cross product like this. We write down ijk across the top and crank it out like we're doing the determinant, okay? And that will give you the cross product. And these, of course, these notation means you actually are calculating the determinant. And so next, let's look at certain terms that you haven't seen maybe for a while. What is the minor? The book mentions the minor. What's the minor of, say, the term A11? The minor is the stuff that's not in this row or column that is going to multiply and etc. in order to get the determinant is the minor. And the cofactor is the minor, except there's a sign in front, and the sign is directly related to the coefficient of A. That is, if it's 1, 1, then you use 1, 1 to calculate what the sign is positive or negative. So cofactor and minor are very close to each other. It's just cofactor has a sign to it. And again, that has to do with calculating the determinant. You know how it goes plus, minus, and I'm always messed up in there. Anyway, so that is that. Okay, so that's all I want to say about the determinant. And next, what I want to remind you of is all the properties of the cross product. All right. Now, cross product is also taught in, I don't know, Calculus 3. Is from what I remember talking about it. But doesn't matter where you talked about it. The cross product has these properties. I just want to refresh your memory real quick. First, if you flip it around, you have to slap a negative sign in front. Okay, that's just how it works out. Distributive property does work. If you cross something, you can you can cross each one. But remember, you can't flip things around, because if you flip it around, then you got to slap on the negative sign. So multiplication by a constant does go in. Okay, the constant is able to go into each vector being crossed. And the zero vector, crossing a zero vector is 0. Crossing with itself is also 0. Okay, and then there's those. And the next two things are less commonly mentioned. One is the triple scalar product. We'll talk about that later, which that was mentioned in Calculus 3 class I taught. Triple cross product was never mentioned, but until later. Okay, but it's a thing, and we'll also talk about this, I think, in a moment. So finally, there's a definition of the magnitude. Remember, the cross product, the magnitude of the cross product. Oops, my camera is passing out. Okay, the magnitude of the cross product is AB sine theta, whereas the dot product is UV cosine theta. Okay, so remember all this stuff. All right, so now we can start with the book. So for the first couple of pages of the book, this is page 62. That's where we're starting at. Okay, now 62, we have let's see. for page 62, please read this yourself because it has a short review from the ground up of what is a vector. And then 63 is similar, okay, all the details of what is the magnitude of vector, what is a null vector. The word null in advanced math means 0. So a null vector is just a 0 vector. And then and so on. Now this please read all this yourself all the way to the end of this page. Okay, both of them, being that they're reviews, so I'm not going to repeat it. Specifically, I want to draw your attention that the book wants to use in the middle of the page where it says letters R, S, T, U, V, W, alpha, beta, gamma will be used for vectors. Okay, in this chapter, and then the letters K, L, M will be used for scalars. Remember, scalar is a number, whereas vector that is a scalar is a number that isn't a vector. Okay, so then there are all these properties that are fairly straightforward especially about the dot product. And the cross product is, of course, more difficult, but I have just mentioned some of the ones that you already have learned in the past. Okay, and so please read these 2 pages carefully yourself, and then we'll continue to the next page where we'll see something super interesting. So now let's look at the next page. The next page, the first thing that is neat is that the determinant from now on will be called parentheses RST, where RST are the vectors written vertically. Okay, for example, the determinant, notice the parentheses. When you write parentheses around 3 vectors, that means that means the determinant, period. Okay, which I thought is a neat way of saying that. Okay, that is so the determinant is well, whenever you see that, it means that. All right, and then so the next thing, if we're going to calculate it, that is calculate the determinant, we will have equation 2, whereas our ST is the same as our dot ST. I mean our dot S cross T, sorry. And to know that, I have some of it written out. Okay, if you do our dot S cross T, the determinant is S cross T written vertically. But remember, when it comes to determinant, doesn't matter if you write it vertically or horizontally because the transpose is equal. Okay, so I wrote it vertically so that you can do the multiplication easier or something. Well, whatever. The point is, what are we doing? Let me see. What did I mean by this? Well, actually, there's no easy doing the cross product. Okay, either way, it's going to be hard. So I just wrote it out that I think is easier for you to stare at. So so please stare at this thing until you realize that this is true. Okay, and that is the determinant is the same as R dot S cross T. If you do S cross T in the first one, and then the same as, which end up being the same as S dot T cross R, which is the second one. And the third one is T dot R cross S. I didn't even bother writing it down. You can write that yourself. And you don't have to check all of them, maybe just, a few terms until you're satisfied that this does work out. There is no magic to this. It's just a matter of, like checking stuff out to make sure it does work, like it says. And from from that, we have the triple scalar product, which is R dot S cross T, end up being R cross S dot T. That I got that by reversing the last term, because the dot product, you can reverse it, right? So it becomes this thing becomes R cross S dot T, and that is the triple scalar product that we mentioned a bit earlier. That was proved in the earlier calculus, but we will also prove that here, I think. Yeah, a little bit later. So anyway, as a result of equation 2, you notice that RST, which is R dot S cross T, being that is equal to S dot T cross R, RST is the same as STR. In other words, you take, what? Let's see, R got shift to the end, right? You see, R is at the first position, and it got kicked to the end, whereas ST got moved forward. So you kick the first term to the end, basically is the plan here. So the determinant of RST and STR are the same. And similarly, then if you kick S to the end, then TRS now is the determinant. Okay, and they're all the same because of equation 2. And so, so there's that neat trick that you can do to determinants by kicking the first column into the last position, and then the determinant doesn't change while everybody else move forward. And so the next thing we need to look at is the Lagrange identity, which I don't think that was proved in the earlier classes. Okay, this is the first time we look at it, and we are going to look at it like this. And that is a quite a complicated situation, right? You have to do the cross products and dot products, and they have both sides. And we're going to end up a whole pile of stuff, which is right here. And I copy and pasted this from the internet. Okay, if you're interested, you can go ahead and multiply that stuff out yourself and to convince you. But there is no trick to this. To prove the Lagrange identity, you gotta work out both sides and then see that they're the same. That's about all there is to do. Now, the triple cross product that you may or may not had earlier is similar to the Lagrange identity in the sense that is some equation that happens to be the same on both sides. And the way you can do it is by calculating it brute force. Just crank the whole thing out. Like I copy and pasted this answer from online, okay? And then, and you can, if you are interested, you can go through all that work yourself. And the reason I wrote down the 1, 2, 3 here is I find that slightly easier to apply this formula. That is the first position, second position, and third position variables in order. And then I just plug it in that way. So for example, this is the, when we, R cross S cross T in the next part is being that is equal to negative of something, okay, negative S cross T cross R, and then if we plug it in here, it equals to this stuff, okay, in the order of, so then what I mean here is if you think of, so now S is the new R, right? Instead of thinking it that way, just think about position 1, a variable in position 1 will go here, okay, and variable in position 2 will go here, etc. To follow that formula a little easier. In my mind, you don't have to do that, okay? Just do whichever way works for you. So anyway, by the time you work this thing up, plug this equation in, apply it here to get this equation here, so then you notice that it is not the same. That is, R cross S cross T, you can't move the parentheses, okay, unfortunately. Whereas the similar formula, the triple scalar product, you can. See, with the dot product, you can move the parentheses. The triple scalar product means you can move the parentheses. You can't move the order of the stuff, but at least you can move the parentheses. Whereas the triple cross product, you can't even move the parentheses. It just, yeah, it is not gonna, it's just not the same. So it's not associative. Now, so that is that. Now the next part of the book, so again, please read this carefully. Okay, now we're at the towards the bottom of page 64 that we're on right now, where the book mentions a neat trick that if we are to prove two vectors to be equal, one way we can do it is multiply that the two vectors by some random any random vector. Let's call it W. For example, to prove that our vector R equal to vector S, we're going to dot it with some random thing, okay, such as W. For every vector W. Now, if they are equal if you can somehow prove that they're equal for every W, then the two vectors R and S has to be the same, because there's no way they can dot everything and still be different, okay? So if they behave the same way with everything, well, specifically if we can prove that R dot W equals to S dot W for every vector W, then we can choose W equal to 1, 0, 0. Then that will immediately mean R1 equal to S1, and then we choose the next coordinate, okay, a unit vector, then R2 equal to S2, and R3 equal to S3. That means they are definitely the same vector. So that is, yeah, where am I? Okay, and so that as the next lesson, we are looking at page, what is that, 65 now. So on page 65, we're going to prove something. I thought, okay. So on page 65, let's look at example A, okay? Look at example A. We will prove some kind of a, we're going to prove the triple cross product, but we're not going to do it the hard way like I just showed you. We're going to use the Lagrange identity and all the other stuff we used, and because the reason is because the two formulas are sort of built on each other, so if we already got one, then we don't have to work so hard to get the other one, okay? So assuming that we have already worked hard and got through all 12 terms of the Lagrange identity proof, and and so how are we going to prove the triple cross product? With the help of the Lagrange identity, which I copy and pasted right here. Now first we will use equation 2 on the previous page, where it said that RST, the determinant, okay, is R dot S cross T, which is, which end up being, according to equation 2, S cross T dot R, which is also RST, right? Anyway, that is, you can, that is what equation 2 says. So then, so what are we proving here? Oh yeah, the triple cross product. Okay, moving on. So let's, so that is, so next, I quote a Lagrange identity here, which let's bear that in mind. And here starts the proof. First, we'll do that trick that we just mentioned a little earlier. Okay, we're gonna dot this thing with some random w and see what happens. If it equals to the other one, for any random w, then we're done. So R cross S cross w, we're going to dot it with a random w. So R cross S will be the new S in this formula right here, the red one. First, we'll compare the red formula. So following the red formula in the red box, we got this thing. Because this is the new S, so plug it in to the determinant, so that becomes the determinant. The first vector will be R cross S, okay? Is it a new S or new R? Let's see, let me check. Did I write that right? Okay, it is the new S in the formula. That is, we'll put this as the S in the red box, okay? So S cross T, and then W will be the new R. The other side, the determinant, I wrote down RST. Well, that I was not paying attention. It should be STR. That is, remember, if we kick the first column of the determinant to the last position, everything moves forward, it's the same determinant. So that's what I should have done. So so in the box, the determinant, if we call it STR, then that's what is happening right here, okay? So the point is, we have, it will be equal to the determinant of this thing. And that is the same deal. And then following the equation up here, except we'll write the determinant as STR, okay? Kick the R to the end. So that follows the first line, and then the next thing we're going to follow is the first line. That is, now this thing is the determinant because you have the parentheses there, right? And that means determinant of those three vectors. And then following the blue box, then the determinant will be the first vector, which now is R cross S, dot the cross product of the other two. Okay, and so following the blue box formula, then we got a second line. And once we got that is exactly the Lagrange identity. Okay, so we copy the Lagrange identity word for word down here, and even the variables are the same. And then we're allowed to factor out W because it's a dot product, and in dot product you're allowed to factor stuff out. Because dot product acts a lot more like multiplication than cross product. You don't have to worry as much of something going crazy. So we factor out the W, and then we have this equation proved for all, that is, this thing, the left side dotting at random W is the same as the right side dotting at random W for all W. And therefore, by our previous trick, okay, and that if two vectors dot so the dot sum random vector is always going to be the same, then the two vectors are the same. And that's how we proved example A, which is, what was it? The triple cross product. That's right. And so that now we can, so by doing that, we skip doing this, okay? And you can also do it this way, of course, but trust me, you don't want to do it this way. It's a complete pain in the neck. I have, yeah, let's not talk about what I have done. Anyway, so example B, so next let's look at example B. Example B is a cute little example. Let's read this thing. Alpha, beta, gamma are such that the dot product of any two different things will be 0, whereas the dot product of by themselves is always 1. Now, what does that remind you of? That reminds you of the IJK, right? The standard unit vectors, and that's exactly what they do. And furthermore, don't miss this part towards the side of the book. Okay, because the first time I did it, I missed it. I couldn't figure out why this example works. This thing, I'm talking about this thing right here, okay, where alpha, beta, gamma equals to 1. It's written on the side, but it's important. And remember, they multiply together to be 1. In other words, their determinant is 1, and that matters a lot. So we're going to prove, what are we doing here? It says compute gamma instead in terms of alpha. It's more like compute gamma in terms of, well, whatever. We just want some relationship between the two of them. Okay, so let's do that. And we're going to do by pulling that trick. So we're going to take beta cross gamma. Why? No reason. We're just going to do something and hope that something comes out. So we'll take beta cross gamma dot w using that same trick that if we dot w any random w equals to something, then they must be equal without dotting. So then we'll dot the w, and that is by equation something 2. Okay, I wrote it down over here. Okay, by equation 2, this cross product, it does equal to the determinant beta gamma w. Okay, remember the parentheses of 3 vectors means the determinant. And it's easy to forget because this is the first time I look at it, and sometimes I might forget this. But the parentheses means determinant of those 3 vectors. Okay, that comes from equation 2. Okay, please double check here if you have any doubt, and to convince yourself. And that, of course, is equal to the determinant times that thing. Why? Because that thing is given as 1. Okay, at first I couldn't figure out why it equals that. I thought there was some neat trick, and turns out it's just equal to 1. That's why. Okay, so we're going to multiply those 2 determinants together. And I have typed out so you can see it better. Okay, when I have typed out the 2 determinants, and what is that? So remember, being the 2 determinants, we're going to multiply them as matrices first, and then calculate the determinant. So the multiplication result is right here. If you check them each row times column trick, okay, how you multiply determinants, then you will get this fairly quickly. So that is so that all the dot products work out. And the next, remember the quality of these alpha, beta, gammas. They're like IJK. Anything that the 2 different ones dot together is always 0. 2 identical ones always 1. So then that collapses this thing quickly and nicely. Okay, so I got a bunch of 0s and 1s. Now this is what I end up getting. And then that, if you then calculate the determinant with a bunch of 0s, life is much better when there's a bunch of 0s, and then you get that thing I wrote on the side. It equals a -1 times negative alpha dot w, which is just alpha dot w. And then remember what this is. This is beta cross gamma dot w, right? From the very beginning. That's what we started with. A equals to that, etc. So this thing then equals to alpha dot w for all w, all or any or every. So which means by our trick that then beta cross gamma is going to be equal to alpha, and that is the answer to the example. That's what it's looking for, I guess. And so that's how we are able to prove that beta the example B, which I thought that was a neat little example. Okay, and so we have already come to the end of this section. For homework, let me find it. Now for homework, please do problems 1. I can't, let me turn the page. Okay, for homework, please do problems 1, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, this section, this homework is fairly short. It only took me 2 pages or something, 2 or 3 pages to write it out, which is, I think, no, just 2 pages. Whatever. It didn't take me very long to write it out, which is very nice. So please go do the homework yourself, and when you're done, I want to talk about them. So first, let's consider problem 1. I think that is just a quick review of basic calculus. Okay, we'll plug in. I did what the book wanted, except for this part, which the cross product, I used the calculator. The determinant, I used the calculator. I will have I think I already showed you these calculators. Maybe if I didn't, I will have it. Listed in the video description, and so that you can do it by hand or with a calculator. Okay, because I'm not doing it by hand. Goodness, and this is in 1948 when the book was printed, right? So anyway, so next let's look at problem 3, where we have this thing. Oh, we're supposed to prove qualities G, H, and I. So I did that. G was, I think, pretty straightforward. H, we just need that condition, which I showed earlier. That is, in determinants, if you have something that's split up, like my determinant property 0, when you have 2 things added together, you can split them up into 2 determinants like that and then add them together. And that's the property I'm using here, which makes things very, very simple. See? And then being that there's a plus in here, so it end up being that, right? And then we'll just split up the plus into 2 determinants, and that proves this situation. The same as the next problem. This is calculating the determinant. Again, we'll just split it up, and then it becomes 2 of them or something like that. Using the row addition property of determinants. So that is problem 3. And then problem 5, we are trying to prove, we're not proving anything. We're just using properties G, C, and E and all that stuff to prove some equations, which is what I did. You see, when I use property G here, and then and so on, everything and multiply everything out. The thing is, we're doing dot product, and dot product for the most part acts almost identically to the normal multiplication. So then everything worked out very nicely. Of course, the cross product doesn't, so we have to be more careful. But in this case, it still works out about the same. I think I use property H or something, and I end up with that, and I guess that's good enough. Okay, so that's problem 5. And next, let's look at problem 6, where we have what is that? Okay, so then we're trying to calculate if K exists and is it unique. So to do that, we will use the basic, I think, the properties of dot product. Okay, we'll dot it out, and then we'll calculate K. Remember, R dot R is the magnitude of R squared, I believe. And then, I didn't summarize the dot product properties because they're easier to remember. But R dot R is just magnitude R squared because, well, whatever. And then if you divide by S dot R, which is just the number, okay, then K will be determined automatically, assuming something isn't 0 and stuff. Of course, the denominator cannot be 0, but otherwise it will be unique. And so that's that. Problem 7, we have R cross W equal to 0. If for all W, then we can just choose W equal to 1, 0, 0. And then that gives us R3 and R2 equal to 0. Then we choose it 0, 1, 0, and then it will give the other stuff is 0, and so on. So that answer comes out very nicely. So that's problem 7. Problem 8 is something that we've done before in basic calculus. But in here, I want to use the new fancy methods we use. The old method is very short already. Okay, we just, let's see, where's my old method? The old method for problem 8 is we simply use the the magnitude formula for old weight. This is the old weight, right? We use the magnitude formula and prove that if theta is 0 or something, R has to be parallel to S or anti-parallel. Therefore, S is some multiplier of R. But that is, I mean, that's short and sweet. But if we do that, then we haven't used any of the stuff we learned in this section. So I wanted to use the stuff we learned here. Okay, and so we have. So I read it. What I try to use is the triple cross product. So I did it again, and so L cross S is 0, right? So we will use that trick, something about crossing W, and if it being that it's 0, crossing a W is going to be 0 for all W. So then this is the triple cross product formula, which I applied, and it equals to that thing, and it's still equal to 0. So which means that this R dot W times S is equal to S dot W times R. Now S then is, you can then divide because the dot product is a number, is a scalar, okay? It's not a vector, so you can just divide it. So then S equal to S dot W is also a scalar, and so S equal to some scalar and some number times R. So if that's the case, then that scalar had better be constant, right? I mean, S can be equal to two different scalars multiplied by R. So we'll call that constant K. And as a result, S equals to K times R. Now this is slightly longer than the old-fashioned way of doing it, but we do manage to use the triple cross product, and for which I am very happy with. Okay, and so that's problem 8. And next, let's do problem 9 or something. Let me find it. 7. Okay, so next, let's do problem 9, where my marker is all dying, so I should trash them all. Anyway, so problem 9, we have a quick question about alpha, beta, gamma, okay? And now remember that rule I mentioned earlier is these are the determinants. Now the determinant is the same if you kick the first guy into the last position, everybody move forward, right? So because of that, then alpha, beta, gamma is beta, gamma, alpha, which is gamma, alpha, beta. They're all equal to 1 because the first one equals to 1. And because of that, then we can plug into the example the example, what is this, B or A or something? Well, it doesn't, B, I believe. And then we can replace all other conditions are symmetrical, which means we can replace alpha with beta or gamma or whatever, and then come up with the exact same solution. Then how we prove the rest of it. Okay, so all three conditions will be the same in order. That is, alpha will be beta cross gamma. Okay, the first one, it will be the cross of the second cross the third, in that order. Okay, and etc. Beta is gamma cross alpha, and then gamma is alpha cross beta. And which one did we already do? Doesn't matter. The point is that that relationship works. Now, in the meantime, let's look at problem, next let's look at problem 10, where we calculate this stuff, and we're supposed to prove that alpha, beta, gamma, even if we didn't know that it is 1, it has to be either 1 or negative 1. And to do that, we are going to multiply it by itself. So right now, we don't know what this thing is. Okay, so let's multiply this thing by itself. So I have the two determinants. So the reason we do that is we're going to use that characteristic where alpha, beta, gamma, when they multiply by themselves, they're 1. When they multiply by somebody else, they're 0. Okay, so then we multiply this thing by itself, then we got a bunch of alpha times itself and beta times somebody else, etc. And then we end up having this determinant, which is the identity, and that is equal to 1. Remember, the identity matrix is 1 going down and then 0 everywhere else. Because if you calculated the determinant, then it equals to 1 because everything else disappeared. And so as a result, that means this thing multiply itself has to equal to 1. So this thing equal to plus or minus 1. Okay, and so if it's minus 1, then everything just you just slap a negative sign to the answers on top. Okay, that is all. So that is problem 10. And yeah, and then we will do problem 11, which we have, what is that? Whatever it is. We are multiplying something, right. Problem 11 is even shorter. Okay, this is just the dot product, which everything multiplies nicely. Okay, there is just like a regular multiplication in algebra, and then they end up being the same because an item dot itself is its magnitude squared, so then it end up being 0, like they wanted. So that's problem 11. Let's see, now I need to find the next one. Problem 12. Where's 12? Give me a second. So problem 12 is more tricky. It says something about minimum and how are we supposed to know that work with minimums. Well, let's work it out anyway. What happens is you have the first thing squared and then plus the second thing squared. Okay, and that's supposed to be equal to the third thing squared, right? And what is the third? And what does that remind you of? And there's only one thing in the world that does that, and that is the Pythagoras theorem. Now let's draw this out, okay? And look at my little picture here. First, when you add vectors, okay, so we have, I drew R here, that's the result, okay? And then we draw Ks is over here. So how is K? So then the third corner, so is the end to beginning is R, the R plus Ks, right? Because U plus V is the end to, what is this? The end to the tip, okay? When you have U plus V is how this is calculated. So R plus Ks similarly is going from bottom of R to the top of Ks. The question is, how do we minimize R plus Ks? Well, the only way this thing is going to be minimized is if it's if this point is perpendicular to the Ks. That is, you draw Ks backwards and then until to the point where it is, you can drop from the base of R and drop a perpendicular line to the Ks. And that distance is R plus Ks, and that will be minimum. And that is done a long time ago. Okay, I don't remember where we did that, but that is why when it's minimum is if it's perpendicular. Now at that, so we'll adjust Ks such that this distance is the closest, which is when it's perpendicular. I think in geometry or something, it says the closest distance from a point to a line is the perpendicular distance to that line, right? Yeah, that's done in grade school somewhere. No, I mean junior high somewhere, something, and geometry. Anyway, so that's where I got that minimum business. So once we notice that, once we notice that, then what did I do here? Let me look. Okay, so the next thing I did is I multiplied this algebra out. Okay, very soon I end up with this thing right here. So we have R dot R, and then this thing right here, the extra bit. Now what is that? Being that R plus Ks, that part, okay, is minimum when R plus Ks is perpendicular to Ks. So then the dot product is 0. Therefore, this squared, a squared plus b squared does equal to c squared because that part is 0. So that everything worked out. Yeah, you didn't know you're still going to be doing Pythagoras theorem in advanced calculus, but you are. Okay, we've been doing advanced Pythagoras theorem is the greatest math theorem in all time, in my opinion, because we've been doing it since what? Middle school or something, and never got away from it even through calculus, and now we're in advanced calculus and still talking about the Pythagoras theorem. So that is problem 12. Next, we need to do problem 13. What is this? Let me look at it first. Okay, so problem 13, we're going to prove that this particular determinant, okay, is equal to that mess over there. So I tried it. First I tried something, it didn't work, so I tried something else. Now the something else I tried is I used equation 2, so we have 3 things determinant. That's the first thing dot the second item cross the third item. Okay, that's by equation 2. And then the second part, then it become a triple cross product. So I applied equation 4, the triple cross product formula, and which I got that. And then I rearranged things a little bit. And then by equation, by equation 2, then it does look exactly like this thing, right? And what we're supposed to prove. And that is about it. Okay, so just a neat use of various equations that we know, and that should be the end of this section.